Alright, so here's next lesson 3 here, and there's a couple of videos here on lesson 3 for you to, or one video I should say, and we'll get to that, Keplers Laws. But at the moment we're looking at satellites. So satellites, what is a satellite? Well, by definition it's a small object that orbits a large one. Alright, so the moon is a satellite around the Earth's a satellite around the sun, and then of course we got communication satellites and all the rest of the sorts of things. Alright, so, but the thing about satellites is that they all have in common is that gravity is acting. Alright, and so not only does gravity act, but it holds it in the orbit. Alright, so gravity's holding the satellite in the orbit around the body that it's going around. Alright, so let's have a look. So what we're going to do is we're going to approximate with a circle. So many satellites are approximately moving in a circle. So if we do that and say that the orbit is approximately a circle, then we can do some things with that fairly easily with what we know about circular motion then. So what do we know? Alright, so there's in the notes there's a big bit of a gap. So what do we know? So what we know is that we know the speed that the satellite would be going around, call it V, would be the distance that it travels over the time that it takes. Now, the distance that it travels, if it's approximately a circle, it would be the distance around a circle, which we call the circumference, which is 2 pi r, the radius of its orbit, and then the time, well, the time for one surround is called the period. So 2 pi r on t applies for our speed. Now, acceleration, well, there's a whole bunch of things we can use for acceleration, which would all be equal. So our acceleration, well, if it's going in a circle, v squared on r is what we could use. And if we're using this speed up here and we make a substitution, we get 4 pi squared r over t squared. And then of course, if it's orbiting a big central body, then the acceleration would be big G, big M, the mass of the central body, over r squared, the orbit, which of course we know as G, the gravitational field strength. So we can use any one of those depending on the information we've got. And then finally the force. Again, from what we know about circular motion, the force would be mv squared on r. And again, making those same sorts of substitutions for the v squared, we would get 4 pi squared r m over t squared, or big G, big M, little m on r squared, and that would be mass times the acceleration. Alright, so there's a whole bunch of different formulas that we can use to help us do some calculations. So let's have a look at an example. Alright, so here's an example. Optus B is a geostationary satellite, so here's the first thing we need to. So geostationary, what that means is it stays over the same spot on the Earth. So if it stays over the same spot on the Earth, as it said, its period is 24 hours, because the Earth goes around once in 24 hours. So therefore, its period is 24 hours. Geostationary, it's over the same spot on the Earth. So that it revolves at the same rate with the Earth turns. I've just talked about that. Given the mass of the Earth is 6.0 by 10 to 24 kilos, and the mass of Optus B is 1,500. Calculate a few things. So first of all, A, the orbital radius. Alright, this one's a little bit tricky because there's a bit of mucking around, but okay. Period. What is the period? Period is 24 hours. Now, of course, that is 24 hours has 60 minutes in it, which has 60 seconds in it. So that's 86,000, I should say, 400 seconds. All right. What do we know? Well, what we're going to do, what we know is that there's some acceleration, and it's acceleration due to gravity. So what I'm going to do is pick out a couple of these things out of this, and the two things I'm going to pick out are these two. These ones. So 4 pi squared r on t squared and gm on r squared. Alright, so if I pick those two things out, then I get that 4 pi squared r on t squared equals big G, big M on r squared. Now if I do some rearranging, times both sides by r squared, you get r cubed equals big G, big M, t squared over 4 pi squared. Alright, so then to get r, we need to take the cubed root of all of that stuff. Alright, as I said, it's a little bit more complicated. Right, it's just a little bit of mucking around, that's all. So 6.67 by 10 to the minus 11 for big G. The mass of the Earth, you're told up the top there, is 6.0 by 10 to the 24. Minus 11, make it look like that. And we've got the period, which is 86,400 seconds, and we've got to square that. And then we're over 4 times pi squared. And when you figure that in your calculator, you get 4.23 by 10 to the 7 metres, which, to put it in something that's a little bit more recognisable to us, is 42,300 kilometres. Alright, so there's part A. Part B is asking about the gravitational field strength at that distance. So the gravitational field strength, G. So I'll go back to that long list of stuff. So the gravitational field strength, the easiest one for me to use is that, because I now know what the radius is, and I know a few other big G and big M. So G is big G, big M on R squared. and so that's 6.67 by 10 to the minus 11 times the mass of the Earth, 6.0 by 10 to the 24. Now those sorts of constants like the mass of the Earth and that, you'll be given those. You don't have to remember those sorts of things. They're always given to you, those physical constants. The radius that we just worked out, and we've got to square that, and then we stick all of that in our calculator. And we find that 0.22 Newton for every kilogram. Alright. The next part of the question says orbital speed. So let's come back up here, orbital speed. And so I've underlined those, the orbital speed, there it is, 2 pi r on t, so we know those things are the radius and we know that it's period. So c is v equals 2 pi r on the period, so 2 times pi times the radius, which was 4.23 by 10 to the 7 over the 86,400, and when you put that in your calculator you get 3.08 by 10 to the 3 meters per second, which is a lot of meters every second. So it's 3,000, bit over 3,000 meters every second, or 3 kilometres every second, so very fast. Alright, part D. What's part D got to say? Part D says it's acceleration. Alright, acceleration. So D, acceleration, what's its acceleration? It's due to gravity. Because gravity's the only thing that's acting on it. So A is equal to G then, which is equal to, if we go back to part B, 0.22, 0.22, and you just need to put the right acceleration units, meters per second squared. Alright, so that's the next. So we can use circular motion stuff to help us with our satellites. Now, there was a fellow named Kepler, and this is what there's a video about Keplers Laws. And he came up with some laws about planets and things and what they do when they... So his 3 laws of motion. So his first one was elliptical orbits. So that was his first one. The second one was equal areas in equal time. And his third one is that for every planet, then something that's rotating around it, r cubed, and it takes a certain period, is equal to a constant. Now, that's for each planet. So if you go to a different planet as you get a different, so like the Earth around the Sun, there will be a certain constant, but the Moon around the Earth, that constant would be a different value. It would still be constant. Alright, so what does that mean? So let's have a look at the diagram. Alright, so the first one's pretty, of these laws, the elliptical orbits, that's pretty self-explanatory. So there's an ellipse. So here's a planet going around the Sun, goes around in an ellipse, the Sun's at one focus, there's another focus over there. Don't need to worry too much about that, but at the moment. Elliptical orbit. The second one, this is the interesting one. So equal area in equal time. So what he's saying is the time that it takes this planet to go from L to M, if we go back to the Sun, that order area that's called B, if the same time the planet goes from R to S, so the planet, the time that it takes to go there and the time that goes there are the same, those times are the same, then those two areas are the same. So quite clearly down here from R to S, it's a further distance. So the planet's actually accelerating and goes faster here than it does there. Now when you look at that, that kind of makes a bit of sense, because if the planet's out here, it's that far away from the Sun, but when the planet's down here, it's only that far. So it's a lot closer to the Sun, so there's been a change in gravitational potential energy. And so what happens is that gravitational potential energy is converted to kinetic, and it travels faster here. So what do we need to know? We need to know equal time, equal areas. Right, so let's clear all those drawings and look at the next one. So the next one, this is here r cubed on t squared. So r cubed would be the average orbital radius and the period that it takes. So what he's talking about, average orbital radius, the time that it takes to go around that particular thing, is a constant. Now, that third one has been used on exams a bit, and so we can actually use it's derived from the following. So if you have a force acting, and the force is big G, big M on R, this is the universal, alright, R squared I should say, and acceleration, alright, acceleration is mv squared on R, and also 4 pi r times the mass over t squared. Sorry, not acceleration, that's the force, isn't it? My bad. Mass times acceleration. So that's the force. So there's our force. So we can, and because it's, so this is our circular motion stuff, and this is our universal gravitational force. And because these satellites, remember satellites, it's the gravitational force that makes them go around. So if I take this bit and this one on the end here, and I put them and equate them, I go that big G, big M, little m on R squared is equal to 4 pi r little m on t squared. And so what we then get, if we divide both sides by the little m, that goes times divide both sides by 4 pi times both sides by r squared, and you get r cubed on t squared. Alright, so I said originally that was constant, and so here's actually what it depends upon. So it depends on the universal gravitational constant, 4 pi, all those things are constants, but here's the big thing here, the mass of that central body. Alright, so that determines, it's the mass of that central body that determines what this r cubed on t squared. Alright, so it's a constant, but it's not a universal constant, unlike the universal gravitational constant. It's constant for a central body. Alright, now speeds of satellites. There's got to be a certain speed that a satellite's got to go. Because what we have is this. Right, so here's a diagram. So here's our satellite or whatever it is sitting up here. So say for example we're on a high hill or something and we throw something and generally what we are used to is things going like that. Alright, so it falls towards the earth. However, if we could throw it fast enough, it could go around the earth and whack us in the back of the head. If we threw it too fast, then off it would go. Alright, so there's got to be a certain speed, and this is v, that the thing has to go. So let's have a look and see what we could do. So what we know is that for circular motion, the centripetal force is equal to the gravitational force. So mv squared on r is equal to big G, big M, little m on r squared. The little m's cancel, timesing both sides by r means we get big G, big M on r. So the speed then that the satellite has to go is the square root of that. So the speed of the satellite depends upon the universal gravitational constant, how the central body, how heavy it is, and the radius of the orbit. Alright, so let's have a look at an example. And alright, here's an example. So Ganymede is the largest of Jupiter's moons. There's its mass, and there's its orbital radius, and there's its period in seconds. So it says use Kepler's third law to calculate the orbital radius of Europa, another moon of Jupiter. Alright, so this is where Newton's third law. Right, so that's r cubed. Started using the lowercase there. I should use r cubed on t squared is equal to some constant. Alright, and so I'm going to do two colours. So Ganymede is that red there, and so it has an orbital radius of 1.07 by 10 to the 6 kilometres. So in metres we need another, that's 1.07 by 10 to the 9 metres. So we got 1.07 by 10 to the 9 cubed over its period, which is 6.18 by 10 to the 5 in seconds. And then for we want to know the orbital radius of Europa, and that's in the green, and here's its period. And so that's r cubed over its period. Now I've forgotten to square this bit here. That's bad. So its period is 3.55 days times 24 hours times 60 minutes times 60 seconds, and that's squared. And so then you need to be doing some calculator manipulation. Alright, so what then you end up getting is 6.7 by 10 to the 6 metres. Alright, So the next bit is the orbital, use the orbital data for Ganymede to calculate the mass of Jupiter. So what we can use is we can use this thing here. Alright, so we can use this, big G, big M on 4 pi equals R cubed on T squared. So, big G, big M on 4 pi equals R cubed on T squared. So 6.67 by 10 to the minus 11 times the big M over 4 times pi equals what we got up there, 1.07 by 10 to the 9 cubed over 6.18 by 10 to the 5 squared, and then use our calculator and we solve that. Alright, and when we come out with that, you got 6.0 by 10 to the 26 kilograms. Now, while I was just doing that calculation, I noticed that I'd entered some data in the previous one incorrectly, and so I'm actually in part A a few powers of 10 out there. So yeah, the numbers that I've got written, but I keyed in one incorrectly. And so that should be 10 to the 8 there. Alright. Calculate the orbital speed. Alright, well, there's a few different ways that we can do the orbital speed. Big G, big M on R would be one of those, the square root of, so let's have a look at that. So big G, big M on R. So when we do that, we're looking at the square root of 6.67 by 10 to the minus 11 times 6.0 by 10 to the 26 over the orbital radius of Ganymede. Where are we? There we are, 1.07 by 10 to the 9. We stick all of that in our calculator, and we get an answer of 6,115, and that's meters per second. Alright, so there's Kepler's laws and satellites approximated by circular motion, even though we don't know, but even though we do know that they're not quite circular, for our purposes makes life a lot easier. Alright, so text questions, anything you didn't understand, make sure you ask. Also, there's that Kepler's Law video for you to watch. And, oh yes, anything, of course, anything in your notes that you've missed, my notes are on the website. That last example I did a little bit differently in my notes than I did here, but it all works out the same.